Hi everyone. In this video, we'll review some of the basics of integration, including the definition of the Riemann integral and a couple of results about integrals, including the fundamental theorem of calculus that you would have learned in a calculus or introductory real analysis course. So to begin, the notion of the integral really relates back to sort of a fundamental question of finding area. The integral gives us the signed area under a curve, but more generally, as we start our discussion, we might want to just sort of think back, how do we find areas even of, say, irregular shapes, right? So if I gave you, this, and I haven't put any measurements on here, right? So there's no way of actually finding the area of this. But if you had some measurements here, you might begin trying to find the area by decomposing this into shapes that are slightly more regular, right? So you might, for example, think about subdividing it into, say, some triangles and a rectangle or some sort of parallelogram here, a triangle over here, right? You might sort of decompose it into all of these different shapes, each of which are simpler regions to find the area of. Well, similarly, we want to take sort of the same approach when we're trying to find the area under a curve. So say we had a function f, right? And we wanted to find the area under this curve between A and B. We might want to decompose this region into simpler shapes. Now, um, of course, I guess you could try drawing a circle as a simpler shape, right? So you could try maybe filling this area with circles. Of course, this actually becomes a very hard problem mathematically, and how do you pack circles most efficiently? And even if you pack circles efficiently, there's going to be small gaps remaining, right? So it's sort of silly to try and pack circles in there. Um, so you might try, right, just rectangles. They're a little easier to stack together, but then inevitably you sort of run into the problem that you're never going to exactly subdivide this into rectangles, at least not if you have some function that has some sort of curvature to it. So we sort of give up immediately on the notion that we're going to be able to exactly uh, subdivide this into regular shapes that we can find areas of. And we sort of start off by trying to approximate, right? So the first thing we're going to try and do is approximate it by taking sort of some rectangles. And I could take all sorts of rectangles here, right? That sort of roughly approximate this area. Um, Maybe this is one such set of rectangles. So if I was to sort of take this set of rectangles here, right? And if I had a ruler, right, I could calculate the area of each of these rectangles, and that would give me a rough approximation of the area under this curve. Now, obviously, there is some error, right? I am missing, for example, capturing this little bit of area here and this area up here. Likewise, I'm sort of overestimating some area up here and in here and over here, right? So this is only an approximation. It's not a anything definitive. So what we want to do first is we want to write down the appropriate definitions to talk about building this sort of estimate, which we call a Riemann sum. And then we want to define the Riemann integral as an appropriate limit of Riemann sums. So to start with, if we are going to try and build a Riemann sum, we need to define these rectangles. And to define rectangles, you need a base and a height. We're going to start by first defining a partition. The partition is going to be a partition of our interval AB or of our domain. So formally, a partition of the interval AB is some set of n plus 1 values. I'm going to call this set of values P. And we'll call the values that are in P x sub I. So x sub 0, the first thing in your partition must be A. It has to be the left-hand endpoint. The last thing in your partition, x sub n, has to be B, the right-hand endpoint. And then the x sub 1, x sub 2, x sub 3, so on and so on, those are just an increasing sequence of values between x sub 0, which is A, and x sub n, which is B. So visually, you can imagine, right? So I have my function here. It's doing whatever. It could be negative at some values. Here's A and here's B. And so I'm picking a partition of my interval AB. So x sub 0 is just going to be my A. And then I'll come over here and I'll pick an x sub 1. And then I'll pick something slightly bigger, x sub 2, and then x sub 3, and so on, right? All the way until I get up to my last value, which is going to be my x sub n. Now notice I've drawn this here, and it's not just my poor drawing skills, right? There's no requirement here that this partition be uniformly spaced, right? So the distance between x0 and x1 is larger here than the distance between x1 and x2, right? All of these sort of have different distances, but I'm going to use these partition values to divide my interval AB up into n subintervals, and then this gives me sort of all the bases. So each of these now gives me some width. I'm going to call that the delta x sub k. So here, for example, this would be delta x1. That's the width of this interval here, right? It's just x sub 1 minus x sub 0. And in general, I'm going to define delta x sub k as x sub k minus x sub k minus 1. All right, so the partition tells me how to break up my interval into sort of little bases of rectangles. The next question becomes, how do I figure out the height of my rectangle? Well, um, I guess if we weren't worried about approximating this very well, we could just sort of take any old random height, right? I could just come here and I could make that the height of my rectangle. But that's obviously sort of a silly height to choose, right? It has nothing to do with the function value. Now, in a calculus 1 or 2 course, whenever maybe you first saw something like this, you probably learned a left-hand rule and a right-hand rule. So left-hand rule was, we'll just make the height of the rectangle the value of the function at the left-hand endpoint, or f of x0 in this case. That would have been the left-hand rule. The right-hand rule would have been, choose the height of your rectangle to be the function value at the right-hand endpoint, right? And then you might have learned a midpoint rule, which was, well, take the average of x0 and x1 and choose the function value there. So that would have given you a rectangle sort of like this height. Okay. Now, it actually turns out that we sort of feel like it shouldn't matter where we choose that point. It should be one of the function values that occurs between x0 and x1, including x0 and x1. So what we'll do is actually on each little subinterval, I need to do a little reconstituting of my graph here. So what I'm going to do is on this subinterval between x0 and x1, I'm going to choose some value in here called C1. Now C1 is going to be either a sample, we'll either call it a sample point, or more often I'll refer to it as a tag. So there's a tag of this partition. C1 is one of my values between x0 and x1. And that's going to tell me where to take the height of my rectangle. So in this case, the height of my rectangle would just be f of C1 on this first subinterval. Now, I'll keep doing that for each of the subintervals. For each subinterval, I will pick a tag. So I will choose C2 from the subinterval x1 to x2. I'll choose C3 from the subinterval x2, x3. In general, I will choose CK from the subinterval x sub k minus 1 to x sub k, and I'll do that for every k between 1 and n. So for each subinterval, I will pick a tag, and then that tag will help me determine the height of my rectangle. Okay. All right. So all of this has really been just basically 2 definitions. The definition of a partition that defines all my little subintervals in the domain, and tags, which are points selected from each of the subintervals, which help me determine what eventually will be the height of my rectangle. Well, now that I have that, I can actually define the Riemann sum, right? So let f be some function that's defined on AB. Then the Riemann sum of f over the partition P sub C, so that's a partition and the chosen sample points or tags, is given by this sum. So the sum k equals 1 to n of f of ck times delta xk. So, right, this sum is simply adding up, right? If I were to expand this out, right, this is really f of c1 times delta x1 plus f of c2 times delta x2. And if I look at this, right, this is just the area of the first rectangle, right? So if I come over here, right, this has width delta x1, height f of c1. So f of c1 times delta x1 is equal to this area here. Okay. Same thing here. This is area of the second rectangle. And then this sum, right, just continues on until it gets to the last one, f of c n delta x n. So all this sum is doing is adding up the areas of each of these little ones. Now, again, I'll point out to define a Riemann sum, you must have a function on some interval, a partition of that interval, and tags for that particular partition. So there's sort of three levels of things you have to choose in order to define a particular Riemann sum. So I could change this Riemann sum by keeping my function the same, keeping my partition the same, but just changing the tags. I could change the partition, which would then necessarily potentially change the tags, right? So there are lots of different Riemann sums. Even if you keep the function the same and the interval the same, you can have lots of different Riemann sums as that partition and set of tags changes. Now, that's actually good, right? Because what we want is to make a really good approximation. So you see here, right? You sort of feel like on this first subinterval, any tag I choose, it's not going to be a great estimate of the area, right? Because there's going to be some overcounting and undercounting of area. Now, you could probably choose a particular, actually, definitely here could choose a particular C value where the sort of overestimate and underestimate cancel out, but you don't really know exactly how to do that. And there's no systematic way of like knowing for every function how to easily pick that C value. So what you actually want to start doing is actually shrinking down the widths of each of those rectangles, right? Because notice that if I were to come over here and say I chose x3 and let me draw an x4 here, imagine I chose those really close together, right? Well, now my rectangle here, right? Whether I choose the left-hand endpoint, the right-hand endpoint, somewhere in between, the difference, like it's not going to change the height of the rectangle that much, and the error is going to be very small, right? And regardless of where I choose that tag, it's going to be fairly small. So what I want to imagine doing is eventually I want to shrink the widths of all these rectangles down. Now, there's sort of two ways to think about this. Now, the way you often think of this in a calculus course is, first of all, in a calculus course, it's often sort of stipulated that all the functions you're dealing with are continuous. Notice that we're making no such assumption here. And it's also then stipulated usually that you're going to take a uniform partition. So, you're going to pick a width and just sort of every rectangle is going to have that same width. When you do that, then you can just say, well, I'm going to take more and more rectangles. Because in that case, taking more and more rectangles necessarily means all of the bases are getting small, right? If I take this interval and I subdivide it into 100 rectangles, and they're uniformly spaced, then all of those are going to be relatively small. On the other hand, if I don't require a uniform partition, which I'm not requiring here, and I don't necessarily know that my function is continuous, I've got some other things I need to be worried about. So potentially we don't, or well, we don't want, not potentially, we don't want to just take more and more rectangles because it's possible. I'll show you, sort of illustrate this here in a second. Right, if I had some interval here, A to B, I could just take more and more rectangles. Like I could first add a point there, and you're going, oh, okay, those are uniformly spaced. That's good. And then add a point here, and then add a point here, and here, and here. And every time I could subdivide the last interval. Well, then if I go to approximate the area under my curve, I start drawing rectangles here. No matter what I do, like this is probably not going to be a very good estimate because this base, even though I've added more and more and more rectangles, in doing that without a uniform partition, there's nothing forcing this base to get small. So what we actually want to do is we want to force the bases themselves to get small. Now that will necessarily mean adding more and more rectangles, but it's a one-way implication. If you force the bases to get small, then that will necessarily mean you have more and more rectangles. If you force more and more rectangles, that does not necessarily force all of the bases to get small. It would force some of them to get small, but not all of them. All right. So with that idea in mind, we now want to define the Riemann integral. So again, take a function f defined on the interval AB. Then the Riemann integral of f over an interval AB, if this limit exists, is given by the Riemann integral from a to b of f of x dx is equal to, now if we ignore this limit piece for a second and just focus on this sum, notice that this is just some Riemann sum, right? So I want to take the Riemann sums and I want to look at what happens to them as the limit of, this is the norm of the partition goes to 0. And we define down here the norm of the partition. So the norm of the partition is just the largest width of any of the subintervals, right? So if I take the norm of my partition going to 0, what that means is that the biggest subinterval is still getting smaller and smaller and smaller. So that's forcing, if the biggest one is getting small, then all the other ones have to be getting small as well. So the idea is take Riemann sums, but then look at what happens as you take these Riemann sums over all these partitions where the norm of the partition is getting smaller and smaller and smaller. Now, conceptually, this is a good way to think about it. When it comes to actually proving things a little bit later, we'll need to work a bit on this definition because you'll notice that this is not necessarily a limit in the conventional sense that we're used to. We're taking a limit here as, well, these P sub C's, those are tagged partitions. So that's like sets. And so as these sets, as their norms go to 0, that's not like some real number approaching 0. Although the norm of that partition is a real number, but you've got it over many, many possible sets. So we'll need to make this a little more rigorous later on, which we can do. But the idea remains, I just want to force the widths of those intervals to get small so that I can make sure that I'm getting better and better estimates. And then as I do that, if these Riemann sums are converging to some value, then that is the Riemann integral that I want. Now, again, this is a great conceptual definition. Later on, we'll build upon this to come up with a definition we can prove things with. It is a horrible definition for trying to actually calculate anything. It becomes very, very difficult beyond a few sort of basic examples of like integrating the function x or x squared or maybe x cubed. Some monomial type functions or you can do this with, but beyond that, it becomes very difficult to even deal with these series, much less than take a limit of those series. So that's quite tricky to actually compute anything with. So, right, what did we do in calculus? Well, you looked at this, you saw the definition, and then we started learning some rules. Okay. So the first thing you probably were told, right, is, okay, if you have you learned some sort of algebra of integrals, right? So if you had two functions f and g that were both integrable on some interval a, b, and if c was some constant, then if you had the integral of a constant times a function, that was you could pull the constant out of the integral, right? And if you had the integral of a sum or difference of two functions, two integrable functions, then you could break the integral up over the sum or the difference, right? So these are fairly basic properties, right? You pull out a constant, you can break it up over sums or differences. Again, if this means anything to you, that says something about integration being like a linear operation on some set of functions. So again, there's a little linear algebra tie-in if you've seen that before. But let me just point out, right, sort of if you think about why this works, right? And this is not a full proof, but if I think about what this is, right? This is defined to be the limit as the norm of partitions goes to 0 of the sum k equals 1 to n of, okay, now it's going to be my function, which is c times f of x evaluated at my partition values times delta x, sorry, these should be k's. And I started to look at this. Well, this is just a sum. I can factor a constant out of each term of the sum. This is the limit. As this goes to 0 of c times the sum k equals 1 to n of f of ck delta xk. Okay. And I can pull this constant then outside of the limit because I know that this limit that I'm now writing down, I know that this limit exists because I know my function f by assumption is integrable. And being integrable means this limit exists and is equal to the integral from a to b of f of x dx. So what I want to sort of again point out is that all of these algebra of blank theorems, algebra of derivatives, algebra of continuous functions, algebra of integrals, they're really just building upon the algebra of limits, right? And a lot of what goes on in real analysis is trying to understand when things can be pushed and pulled inside or outside of limits, whether they're constants, right? So pushing a constant inside or outside of an integral really works because you can push a constant inside or outside of a limit. Later on, we'll see things that are really things about exchanging limits, right? When can you swap the order of two limits? That's also another big thing that pops up. So all of these are really just going back, all the ones we've seen so far are really things that just go back to the algebra of limits and what we can do with those. So you could construct a sort of similar argument here for the sum or difference, that you just write down what this means in terms of the limit of a Riemann sum. You then apply properties of limits, and then you end up with this. So you can split up an integral over a sum. All right. Now, the major sort of consideration when you start talking about integration is the fundamental theorem of calculus, right? Because in a Calc 1, Calc 2 sequence, right, you talk about all this stuff about differentiation. You introduce this notion of integration, which is sort of totally different, seemingly has nothing to do with derivatives. And then all of a sudden, the fundamental theorem of calculus comes back and ties these two together. So what does the fundamental theorem of calculus say? So it says, let f be continuous on the closed interval ab. Now, one of the results we will prove later on is that all continuous functions are Riemann integrable. So the second we say it's continuous, in fact, it has to be Riemann integrable. But the fundamental theorem of calculus really comes in two parts. So the first part says, if I define a function, capital F of x, as the integral from a to x of f of t dt, then that new function, capital F, is both continuous and differentiable on the closed interval ab, and the derivative of that function, capital F, is just the function little f. The second part of the fundamental theorem of calculus says if I take any antiderivative of f, so just recall f, we say that f is an antiderivative of f, that really just means capital F prime of x is equal to f of x for x in the interval ab. So that's what it means for capital F to be an antiderivative of little f on the interval ab. So if capital F is any antiderivative of little f, then I can evaluate the integral from a to b of f of x dx by just evaluating the antiderivative at each of the endpoints and taking an appropriate difference. Okay. Now, in discussing these, let's actually start with the second one, because this is sort of the one that ends up being most impactful immediately in like a Calculus 2 course, right? Because what this second piece says is if I can find an antiderivative, then I can evaluate the definite integral of any function, right? This immediately turns sort of Calc 2 on its head, because now it turns finding integrals of things into finding antiderivatives of things. And so all the so-called methods of integration that you then learn, they're really not methods of integration. They're methods of taking an antiderivative. So the power of the second part of the fundamental theorem of calculus is that it says that, like, if you look at these two things, on the left here, we have the integral from a to b of f of x dx. That's defined, right, as some limit of a Riemann sum, right? This is the limit as norm of the partition goes to 0 of the sum k equals 1 to n of f of ci delta xi. Okay. So that's some limit of some complicated expression. On the right-hand side, this is something about another function that happens to be a function whose derivative is this function. And oh, if I just evaluate that at the endpoints, that will give me the value of this. When you think about it, like, these two things should have nothing to do with each other, right? On the left-hand side, you have an integral. On the right-hand side, this is something about derivatives. These should have nothing to do with each other. But the reason it's the fundamental theorem of calculus is because it is showing us a deeper connection between these ideas of integration and differentiation. We'll prove that more in depth later on. Now, the first part of the fundamental theorem of calculus, while maybe not as computationally useful as the second part, I actually think it is really beautiful in a different way. So if you look at this, yes, it tells us actually how to define an antiderivative function. Here's one way to come up with a function, capital F, whose derivative is little f. But what's actually more powerful is it actually tells us that that new function is both continuous and differentiable. So we started with a function f that was just continuous, and what we've done is built a function that's both continuous and differentiable. Differentiation does not do this. So you can sort of imagine, for the first part of the fundamental theorem of calculus, if you think about a function like, say, absolute value of x, and I'm not going to draw any axes here, but you can sort of imagine this one. Because if you tried to take its derivative, right? Well, first of all, its derivative is not going to exist at the origin, right? And its derivative is going to be -1 when x is less than 0 and +1 when x is greater than 0. So you're going to get a function that looks something like this, and it's not even defined at 0. Okay, so this gives you 1, x is greater than 0, and -1, x is less than 0. So differentiation took a continuous function and broke it, right? However, this function, if I were to take it and integrate it, I would actually get this function, x times the absolute value of x. It looks like this, which you may think looks like x cubed, and it sort of does, but it's actually not quite x cubed. This is actually like you took a parabola, right? So you took x squared over here, and then over here you took negative x squared, right? That's actually what this works out to. And while it is, it doesn't have derivatives of every order, it is continuous and it does have a first derivative that is actually also continuous. So when I think about this, right, I sort of think about these two spectra, right? Or you have integration going this way, making functions smoother, right? And you have differentiation going this way, which is making functions less smooth, right? So I really like the first fundamental theorem, the first part of the fundamental theorem of calculus, because it really sort of gives us this idea that differentiation and integration, one of them makes functions a little bit nicer in a certain sense, and the other makes functions a little bit worse. You may have come away from calculus with a different impression, though, right? Because integration is often harder to calculate than differentiation, right? But actually, integration makes functions smoother, differentiation makes functions less smooth. Now, hidden within both of these, though, is one final notion, which is that differentiation and integration are almost like inverse operations in some appropriate sense, right? So we think of differentiation as being an operation that acts on functions, and we think of integration as being an operation that acts on functions. Like the first part here basically says if I take a function little f and I define this new function capital F by integrating little f, then if I differentiate that function again, I'll get back little f, right? So they're inverse functions in some appropriate sense. That again is a very powerful idea, and we'll be exploring that later on as we start to prove more theorems about integration. The last thing I want to do is just recall quickly a couple of methods of integration, or as I said before, they're really more like methods of finding antiderivatives that you would have seen in calculus. You may have some chances to practice this in some exercise sets, but I just want to remind you of the idea of these briefly. So the first is integration by substitution. So imagine you have a continuous function f, which is a function of u, and u, a continuous function of x on some interval ab. Then what this says is, we often use this in the other direction. We say the integral of f of u of x times u prime of x dx is equal to the integral of f of u du. So you first might look at this and sort of think like, okay, I mean, maybe this is just some symbolic manipulation. In a way, it is. But what's going on here is actually a pretty powerful thing, which is that this sort of allows us to change the variable that we're integrating with respect to. So I can switch from integrating with respect to u, I can recast this as a problem about integrating with respect to a different variable, u. Performing changes of variables is a very powerful way of transforming lots of different types of problems, from maybe something that's a little more complicated to something that's a little more tractable, right? So when I look at this, let's first just remind ourselves, like, how did this work in a calculus course, right? So you might have been asked to find, say, the integral of cosine of x squared times 2x dx, right? We're just going to do a very basic example here. And typically what you'd do is you'd say, I see a function, there's x squared. That's going to be my u of x. I see its derivative here. That's u prime of x. You may have often, we'll write this as u is equal to x squared, and then we'll just write du is 2x dx, because that's the derivative of x squared. And then we just come down here and say, okay, this is really the integral of cosine of u du. The antiderivative of cosine is just sine. So this is sine of u plus a constant. And this gives me sine of, well, my u was just x squared plus a constant. So this is how we often use this. But, I often tell you it's a little bit nonsensical. I mean, first of all, like, what even is du? Like, that's not well defined as its own mathematical thing. In fact, it's really just like the dx and the du are just some symbols that tell us the variable we're integrating with respect to. So it doesn't make sense to sort of calculate du. Um, so how does this really work? Well, the idea is if I were to look at um, the right-hand side of this expression over here, so if I were to look at the integral of f of u of x times u prime of x dx, I can actually see that this thing sitting right here, if I let capital F be some antiderivative of little f, so let capital F be such that, uh, sorry, that the derivative of f of capital F is equal to little f. So if I take a capital F in that way, then this is just the integral of, well, this expression sitting here is just the derivative of capital F of u of x. So this notation then is saying, okay, I want to take the derivative of this and then take the antiderivative of this. So this just comes out, this is just f of u of x. Okay, or that's one possible antiderivative. There are many antiderivatives. They all differ by a constant. Okay. Now, if I look at this, this is the same thing I would get by just taking, if I just took the integral of little f of u du, right? Well, that would just be, I mean, that's really just capital F of u, an antiderivative of that. So you see that these are really the same thing where, well, I'm just making the substitution, right, that u is equal to u of x. So I can really think of this problem in either way, and often this is an easier way to actually calculate things than this is. Okay, so because of this connection, so I have this is equal to capital F of u, this is equal to capital F of u of x. And through this equivalence, these are the same thing, but recall that this was actually just another expression for that integral there. So integration by substitution is a really powerful tool that, excuse me, allows us to simplify integrals quite substantially in some cases. But it is also limited. It's not a, it's not a perfect tool. It doesn't apply in every circumstance, right? In particular, I need a function and more or less its derivative. You can do some things here if you're off by basically a multiple of a constant or sorry, some constant multiple. You can fix that, but you need almost the derivative sitting here. If you don't have that, then this isn't really going to be particularly helpful. The other method of integration you often learn is integration by parts. So suppose f and g are continuously differentiable. And I've written this in the case that you have a definite integral, but you could just remove the limits of integration everywhere. This would equally be true for indefinite integrals. But this is just the typical integration by parts formula you would see. This really just falls out of the product rule. So if you write down the product rule, the derivative of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. Okay, that's just the product rule. Now I'm going to take an integral of both sides. So integral dx. Over here, I have the integral, the antiderivative of the derivative of a function. So this is just f of x times g of x. And over here, I'm just going to break up this integral over this sum. So this will be the integral of f prime of x g of x dx plus the integral of f of x g prime of x dx. Now, this is analysis, so we have to be careful. How do I know I can break this integral up over the sum? The assumption that f and g are continuously differentiable means that the function is continuous and its derivative is continuous. So I know that f prime is continuous and g is continuous. The product of continuous functions is continuous, and all continuous functions are integrable. Similarly over here, I know f is continuous, I know g prime is continuous. The product of continuous functions is continuous, and all continuous functions are integrable. So I know I can actually do this. And now if I just rearrange this slightly, like I'm going to move this over here. So I'll get f of x times g of x minus the integral of, and I'll just swap the order of these, g of x f prime of x dx is equal to the integral of f of x g prime of x dx. Okay. And well, this is exactly what we have over here, just without the limits of integration. And I guess I've sort of swapped the sides of the equality, but it's the same formula. Integration by parts is a really powerful tool. And even in this course, we may not get to see fully everything that integration by parts is useful for. But I'll just sort of briefly point out one of the things that's really powerful about it is if you look at the left-hand side, you have an integral where inside the integral you have a function's derivative. So you have like g prime, right? And what integration by parts allows you to do is it actually allows you to rewrite this so that you push the derivative onto the other function. So over here, the derivative is now on the f instead of on the g. It's a very common trick to play in the area of math I work in, which is differential equations. It's actually very common to take a differential equation, you multiply it by something called a test function, which is often just a function that has as many derivatives as you need. You multiply your differential equation through by a test function, and then you start integrating by parts because now you can move derivatives off of the unknown function in the differential equation and push them onto that test function. This turns out to just be an incredibly powerful tool to use. Now you need a lot of other theory to help you, and why exactly that turns out to be useful is beyond the scope of what we're talking about today. But this is just a very powerful tool to be able to use. Yes, it's also useful when you're trying to integrate things, like just by hand in a Calc 2 course, but it's also something that gets used quite a bit in lots of other areas of mathematics. We're going to stop here for this video. In this video, we've recovered the definition of the Riemann integral. And we've also just talked a little bit about the properties and methods of integration you would have seen in a Calculus 2 course. Later on, we'll come back to integration, and we'll go through and much more carefully prove some of these theorems and see how to relax some of the hypotheses that have been given in some of the theorems here.